agreement plot or Bland-Altman plot description in SPSS using method 2. Bland-Altman plot, or alternatively called the mean difference plot, is a method to assess whether there is an agreement between two measurements. So the Bland-Altman plot is a graphical method that will examine whether there is an agreement between two different measurement methods and whether those two measurements can be used interchangeably. So the plot is a scatter plot in which the differences between the two measurements is plotted on the y-axis and the mean between the two measurements is plotted on the x-axis. There are three major horizontal lines within this plot. The first line is called the bias or the systematic bias, which represent the mean difference, and the other one, which is the upper and the lower limits of agreement. When to use the Bland-Altman plot? When comparing new measurement method against an already established standard method. Another application of the plot is to assess inter-rater or inter-instrument reliability. The plot also can be used to evaluate repeatability, which is test and retest of a single method. To do the plot, certain assumptions have to be met. Those assumptions are certain criteria or certain characteristics of the data that have to be fulfilled before plotting the graph. The first assumption is that the differences between the two measurements are normally distributed. The measurements are paired, and finally there is no strong proportional bias. If there is a strong proportional bias, then log transformation to the data can be performed. So how do we plot the graph? First of all, we need to calculate the systematic bias or the mean difference. So the mean of the two measurements can be calculated by adding the score from the first measurement and the score from the second measurement and dividing that by 2. And this has to be repeated for each paired scores or readings. And to calculate the difference between the two measurements, take the first score from the first measurement, subtract that from the second measurement. By this way, two new variables will be generated. One is the bias, the second one is the differences. To also calculate the limits of agreement, there is a formula or equation for it, which is for the upper LOA, it's equal to the bias, which is the mean difference, plus 1.96 multiplied by standard deviation of the differences. And to calculate the lower limits of agreement, the equation for that is the bias minus 1.96 multiplied by the standard deviation for the differences variable. These two lines define the range within which 95% of the differences between the two measurement methods are expected to lie. To recap again, there are three vital horizontal lines in the Bland-Altman plot. The first line is the mean difference, the second one is the upper limit of agreement, and the third one is the lower limit of agreement. So how do we analyze the plot? When looking at the plot visually, we will check for systematic bias, look at the LOAS, and look for proportional bias, look whether the data are randomly scattered, check for outliers, and check whether there is constant variance across the scores. The Bland-Altman plot interpretation, we need to check the systematic bias, which is the mean differences, and the systematic bias is a central horizontal line, which is the average. This line will show whether there is a systematic bias between the two methods. If the value for the bias is close to 0, there is no average bias. If the mean difference is greater than 0, then method 1 gives higher values than method 2. If the bias is less than 0, then method 1 gives lower values than method 2. So if the mean difference is far from the 0, then one method constantly over or underestimates. If the difference is scattered randomly around the 0 value, then that indicates a good agreement. Looking at the limits of agreement, if there is a narrow range, then the two methods are closely agree for the most of the measurement. If the range is wide, then there is a poor agreement. Another thing to check is whether there is a proportional bias. To do that is to look whether there is a pattern in the scatter plot. So if the differences get larger or smaller as the average value increases, then this indicates that the two methods disagree more at a high or a low values. To check that, double check that, and confirm this observation, then simple linear regression can be done using the variable for the differences between the two measurements and the mean for the two measurements. As shown here in this scatter plot, there is a proportional bias. There is a trend. When there is an increase in the values for the mean, there is an increase for the values for the differences. In fact, a line can be drawn here to show that there is increased relationship between the two variables. So this indicates that there is a proportional bias, and this can be confirmed by doing the linear regression test. As shown here in the second plot, when there is an increase in the difference, the average increase. So there is a trend in the graph, so that indicates that there is a proportional bias. And the way to resolve this issue is to do log transformation of the data. The other things that to check when looking at the plot and analyzing the plot is to check whether the data are scattered randomly above and below the mean line across the entire range of the average, which indicates good agreement between the two methods. Another thing to check also in the plot is whether there is an outliers. Outliers are extreme low or high values that deviate from the rest of the scores. Here we can see from the graph that there are points outside the upper and lower limit, this dot and this dot. So these are the outliers, and too many of the outliers suggest poor reliability. And also to look for, when examining the plot, whether there is a constant variance. If there is no constant variance, then there is a heteroscedasticity. So the spread of the differences is inconsistent across all the average values. Examining the plot to see whether there is funnel shape pattern which indicate that the agreement getting worse at higher or lower values. To overcome this issue, log transformation or using a ratio plot. As shown here in this two graphs here, there is a funnel shaped pattern in these two graphs, which indicate that there is no constant variances. Once the graph is plotted and visually examined, then further steps can be done to confirm the observation, whether there is a systematic bias or not. Statistically, is to use the one sample t-test for the difference variable and to confirm whether there is a proportional bias. Then linear regression, simple linear regression, can be performed using the dependent variable, which is the differences, and the independent variable, which is the average. Mean difference plot in SPSS. Here in this SPSS data view, there are two variables, two measurements, measurement 1 and 2. And to find out whether these two measurements agree or can be used interchangeably, then mean difference plot can be used to visualize whether there is agreement between these two measurements. In a previous video clip, I had described one of the method to do it in SPSS. This is a second way to do and to draw the mean difference plot in SPSS. You need to have the latest version of IBM SPSS to do and to plot this graph. To draw the Bland-Altman plot, click on Analyze, scroll down to Descriptive Statistics, and then select the Bland-Altman analysis. A new window will appear to allow drawing of the graph. Drag the measurement 1 to this position and measurement 2 to this position. Click on criteria. In the criteria, no changes here will be made, so just click on continue. On the print icon, I'm going to select the mean differences and confidence interval, the agreement limits and confidence interval, and print details of the analysis. Click on continue and then click on the plot. In the plot, I'm going to take the agreement limits, and then if I click on continue and then OK, few tables and a plot are generated. From the second table here, it shows that the difference or the mean difference between measurement 1 and measurement 2 is equal to minus 0.049, which is very close to the value of 0. In the next table, the limits of agreement, the lower limit of agreement is minus 0.87, and the limits of agreement or the upper limit of agreement is 0.773. So this table shows the limits of agreement, the lower and the upper, and this table shows the mean difference, which is the bias or that shows whether there is a systematic bias. Moving to the plot here, which is the Bland-Altman plot of differences between the two measurements. As shown here on the y-axis, the differences between the two measurement methods is plotted here. and on the x-axis is the mean between the two measurements. And in the graph itself, there are three horizontal lines. The reddish line represent the mean difference or the systematic bias. And the two blue lines here, the upper one and lower one, represent the limit of agreement, upper and lower. We'll do some editing for this graph to get rid of these lines here. So if I double click on the graph, a new window will appear here. Double click on these horizontal lines, select this section here, and then click on apply. Close this and close this again. Back again to the plot. As we look at the plot here, we can see it is a scatter plot with the dot randomly scattered in the diagram. And the systematic bias or the red line is very close to the value of 0. And there are few scores or data points that are outside the upper and lower limits of agreement. Fairly from this graph or plot, we can see that these two measurement methods do agree, and they can be used interchangeably, and there is no systematic bias. To confirm this mathematically, we could do one sample t-test on the difference. Before performing the one sample t-test, we need to generate two new variables in SPSS. Back again to the data view, we need to generate two variables. The first variable is the difference between measurement 1 and measurement 2. The second variable is the average between the measurement 1 and measurement 2. The way to do that is to click on transform, then select compute, then generate a new variable and give it a name of diff for differences. And then in the numeric expression, select the first measurement, add a minus sign for subtraction, and then select the second measurement, and then click on OK, and back again to the data view here. A new variable is generated for the differences from each score in these two variables. The difference is calculated and recorded here. To generate the average, click on transform, compute variable, and give a new variable a name which is average, and then erase this numeric expression. In the function group, select statistics or statistical, and then select the mean. In this equation here, drag the first measurement into that position and the second measurement into the second, and click on OK, and back again to the data view. A new variable labeled as average is generated here, which is the average between the scores for each of the measurement 1 and measurement 2. So here we have two variables, the difference variable and the average variable. To move ahead and to do one sample t-test, click on Analyze, scroll down to Compare Means and Proportions, then select the one sample t-test. In this window here, drag the difference into the test variable. In the options, no changes, and we notice here that we are testing that the difference between the two measurement or the variable difference is equal to 0, i.e. the null hypothesis, there is no differences between the two measurements, they are similar, and the alternative hypothesis, there is a difference between the two measurements. If I click on OK A few tables are generated as shown here. The mean and the standard deviation are calculated for the variable difference. The mean is minus 0.048. Moving to the second table, which is one sample t-test. What is of concern here is the p-value, the significant value. Since the p-value is greater than 0.05, then we will have to accept the null hypothesis, which indicate that there is no differences between the two measurements, i.e. there is no systematic bias, i.e. these two measurement methods do agree. So this confirming our observation from the Altman plot. To find out whether there is a proportional bias, then linear regression can be done. And the way to do that is to click on Analyze, select the regression, and then go for the linear regression in the new window here. For the dependent variable, select the differences, and for the independent, select the average. Then click on OK. And a few tables are generated here from the simple linear regression. What is of most important is the coefficient here. We need to have the coefficient, which is unstandardized coefficient, to be as close as to the zero value, and here it is minus 0.07, and we need this p-value to be greater than 0.05. So this table indicates that there is no proportional bias between these two methods. So this is the way to perform Bland-Altman plot in SPSS to test whether two measurement methods agree or not. If you find this video useful, do subscribe to the channel, leave any comment in the indicated box, and activate the notification bell to receive the recent and latest release into the channel of several different video clips, and click on the like icon and share the video link with others so the channel can expand and improve to include a large scope of different statistical method and how to analyze data using several different statistical packages such as SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, GPower, Python, and RevMan. If you are a student or a researcher and you have a data, whether it is quantitative or qualitative, and you want to perform statistical analysis on that data using any of the softwares listed here, whether it's SPSS, Excel, Stata, Jamovi, Statistics, GraphPad, Prism, RevMan, GMP, Python, then do contact me to arrange for either a one-to-one private tutor session or a training course on any of these statistical packages. My contact details are given here, so don't hesitate to write to me or email me if you need a private one-to-one tutoring or a training course.